During this conference school are 1 hour, not 1.5 hours. With different scales, different scale. Previous weeks. So pay attention.
Okay, so first off, I want to very much thank the organizers for inviting me to this, what looks like is going to be a really fantastic 2-week period, and also for the work in organizing it. I'm very excited. Let me give an update. So my schedule next week, I have 2 days where I give 2 lectures each day and 1 day where I only give 1. And because of my topics, sort of one of them is nice as a standalone lecture and my others sort of work nicely together. So I'm going to switch the order of lectures 4 and lecture 6 and lectures 4 and 5, because lecture 6 is the standalone day. So it's the standalone talk. So that comes next week. Everybody okay with that? The next thing is I'll post my notes, and I'll post them to math.utah.edu/Chaika, this is my last name, impam for obvious reasons. So I hope to keep the notes updated there. And then the last announcement is my first 3 talks are going to be all very basic ergodic theory. I figured it was a very diverse audience in terms of backgrounds, so I figured I'd set it up so that I'd sort of err on the side of covering more basics. If you're bored, feel free to leave, feel free not to show up. I understand many of the people know what I'm going to talk about for my first 3 lectures much better than I do. Yeah. Feel free to sleep, whatever works for you. Okay, all right, so, on the flip side of that, because it's unclear what the audience is, if I'm going too fast on the background material for you, you're probably not the only one. Please raise your hand, ask for details. My notes will contain more details, so I'm prepared to say more details, so please feel free to ask for more details if it's something that's new to you or just so wonderful you can't help but see it again. The facts, these classic theorems I'll be talking about. Okay, so let's start with the definition. Okay, so let this be a set, this be a sigma algebra, and this be a measure space. Let T x to x measure 1. We say T is. Oh, another thing. If I write too small, please let me know. We say T is mu measure preserving. If mu of T inverse of A is equal to mu of A for all measurable A. And I think largely, so I think for all that I'm going to talk about these 8 lectures, B will be a Borel sigma algebra on either a sigma compact or compact metric space. And in fact, usually the metric space will be a compact. And T will be continuous and will usually be a homeomorphism. Okay? So, but of course this exists in a much more general world. But if you don't sort of have a background in ergodic theory, you can think of these sort of very kind of more concrete, nicer settings. Yeah, I shouldn't have said nice. Okay, I should also mention, I will basically always suppress the sigma algebra. It will be the Borel sigma algebra, but if at any time you have a question, please feel free to ask.
Your T is invertible, like
no, immeasurable.
Oh,
it's just a map of x to itself. Right? So also usually in this talk I'll be talking about, not only will it be invertible, it will be a homeomorphism of compact metric space, but this exists in a more general setting. Okay, all right, so, and mu will usually be a probability measure in this course. So let's start off with a theorem, the Krylov-Ogolyubov theorem. Okay, so let X comma D be a compact metric space. And T be a map from X to itself, be continuous. Then T preserves some probability measure. So this is a classical result in ergodic theory, and it says that sort of this idea of a measure-preserving map, there's often such an example. It's not just a theory for which there are no examples, there's tons and tons of examples. Okay. And I'm not going to prove the whole proof. There's the proof in the notes, unless by popular demand. If there's popular demand, I'll prove it, but otherwise I'm just going to say what the idea is. So let's say idea of proof. So try and come up with a candidate at notion. So let delta mass for P and X and X, let delta sub P denote point mass at B. So this is a Borel probability measure that assigns measure 1 to a set if P is in it, and measure 0 if P is not in it. Okay? And then so what I want to do is I want to pick any P I have, and I want to look at the sequence of measures delta P 1/2 delta P plus delta T of P, comma, dot, 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 dot. And let me write the general term 1 over n summation from I equals 0 to n minus 1. Am I writing large enough there, or is that too small? All right, delta of T to the I of P. Okay, so by weak star compactness, of the set of probability measures, this is this sequence has a limit point. It doesn't necessarily have a limit, but it has at least a limit point. And then because of telescoping sums, nu is T invariant. A T invariant. Probability measure. Okay, so what you're doing is you're sort of taking empirical measures. You start at a point P, you move forward by the dynamics, and then you take the average of where you started and where you are now, and then you take the next step forward and you take the average of all three of those. And then there's a limit of those. And basically just by telescoping sums, this is a T invariant probability measure. Everyone happy about this?
Maybe for it's worth it to notice that this proof uses the T star X linearly on measures. Otherwise, in other cases, you need to use a fixed point theorem for weak compact, like for parallel for Venus. No, that's a remark. Authors of books write often that if you write precisely the proof, then you use linearity of action of T star.
So I want to make two other remarks. So one is we need compactness. So not true if X is not compact. And then the second one is it's not true if T is not continuous. So what do I mean by this? I mean that there is an example where you have a continuous map of, say, a sigma compact metric space, which has no T invariant probability measure. And similarly, there is a compact metric space and a map on it that only has one point of discontinuity, and yet there is no T invariant probability measure. Okay, so that's some remarks. So this is a really cool theorem that says this is sort of a relevant definition. Any questions at this point? Okay, so let's continue. So let me make a remark. So the measures that arise in this way as these limit points, so definition, T comma X as before, P in X is called quasi-generic. For mu. If mu is a weak star limit point of this sequence of measures. So I'm not saying it's a limit of it, just that it's a weak star limit point. Okay. And more generally, and more specifically, if mu is the actual limit, the actual limit, we say P is generic. And so a consequence, so the Krylov-Bogoliubov theorem basically says that in this nice setting, quasi-generic measures are invariant. Okay? So any questions at this point? So I'll begin the next definition, which is a little idiosyncratic for the purposes of this mini course. And so let T mapping X to itself be mu measure preserving. We say T is ergodic. It is ergodic with respect to mu. If mu of mu of a symmetric difference inverse of A equals 0 implies mu of A complement. So if I have a set that's invariant from the standpoint of dynamics, so of measures, I'm sorry, is invariant from the standpoint of measures. So if I look at a set and I look at its pre-image, and the symmetric difference of those has measure 0, so from the standpoint of measures, the measure doesn't see it at all, then the set either has full measure or has co-full measure, okay? Or its complement has full measure. Any questions on that? So in the case of a probability measure, it would be that the measure of the set is either 0 or 1. So there's no non-trivial invariant sets. I want to highlight, this is a weird definition for ergodic theory. I'm stipulating that it's measure preserving, and that just saves me time always saying that my map is measure preserving for this mini course. So this definition is made in this way for convenience for this mini course. Okay, everyone happy about that? Great. So who's seen the definition of ergodic theory before? Okay, everybody. Okay, so if you look at the notes, there's 7 equivalent conditions for ergodic theory. In the interest of time, I will say none of them. Okay, yeah. Okay, so let me connect this new definition to this definition we had before. So let's take theorem. So let's do some notation. So let mathcal m of t be equal to the set of t invariant Borel probability measures. So I'm in the context I've been in before, where this is a continuous map of a compact metric space. So this is true much more generally, and let mathcal m upper e sub t be equal to the set of t ergodic measures. Borel probability measures. Right. So we have the following theorem. The set of preserved, let's write m sub t is the convex hull, the smallest convex set that contains m sub e of t, and m sub e of t is exactly the extreme points. The set of extreme points. Of m of t. Okay. All right, so what does this theorem say? This theorem says that, it says a bunch of things. It says that my set of invariant measures is convex. That's not hard to see. It's just sort of a consequence of computation. And it says that if you look at this convex set and look at its set of extreme points, that are exactly the ergodic measures. You're an extreme point in this convex set of invariant measures if and only if you're ergodic. Okay?
What does it say? MT is the convex?
Hull. Oh, thank you. Thank you very much. Hull. Thank you very much. Any other questions or typos anyone's noticed? Which I
So this is in general for Borel probability.
Oh, this is very general, yeah. Okay, who's seen this theorem before? Okay, anyone not see the theorem before? Okay, my notes have a proof of it. Yeah, it's a fantastic theorem. I'm sorry, I'm not going to cover it. It's really a great theorem, but maybe I'll just say sort of the big idea of the proof.
You compactness.
So in the setting, so in big generality, this is a compact set. Okay. And in the weak star topology, because it's a closed subset of the probability measures.
The space, X.
Oh, X is compact.
X is
Yep.
You can use function unknown.
Okay, yeah, so what's sort of a big idea of this? A big idea in the proof is that if I have two different invariant measures, and let's say they're absolutely continuous, the Radon-Nikodym derivative of one with respect to the other is a t-invariant function, okay? And having no non-trivial t-invariant functions is an equivalent definition of ergodicity. And this is sort of the key idea in the proof of this theorem, for those who haven't seen it before.
comment that Krivokopolubov or more general theorems can be proven using fixed point theorem just due to convexity with compactness.
Yeah,
So it fits to what is written now.
Yeah, so let me just mention also in context of what you're saying about the connection to abstract results in functional analysis, the fact that it's the convex hull of this is the fact that it's the extreme points and that the assumptions of the Krein-Milman theorem hold for it. And that's how the proof goes. So you've sort of established that the ergodic measures are exactly the extreme points, and then you quote Krein-Milman. Okay? Okay. Okay, so let's state the next theorem. So I'm not going to prove this theorem immediately. I'm going to sort of discuss some of its consequences first. And the main point of tomorrow's lecture will be to give a proof of the Birkhoff ergodic theorem I particularly like, that's due to Katz-Nelson and Weiss. And the notes already have the proof in it, but I really like this proof, but if you know the proof already quite well, feel free to skip. Feel free to skip anyways. Okay, but this is the Birkhoff ergodic theorem. Sometimes called the pointwise ergodic theorem. So let X be a probability space. Let T be ergodic. And F be a function that's an L1 of mu. Then the limit as n goes to infinity of 1 over n times the summation from I equals 0 to n minus 1 of f of t to the I of x is equal to the integral of f d mu for mu almost every x. And moreover, this convergence takes place in L1. Okay? So this is the Birkhoff ergodic theorem. It's sort of a big result in ergodic theory, and it says that if you're an ergodic system, from the standpoint of your measure, the typical point, as it travels around the system, you sort of observe what's happening, and you average those, and it converges to what you see happening over the whole space. Yeah, so this is a really fantastic result. And let me just maybe make a remark that I sort of, when I first saw this, didn't occur to me, but yeah, it should have. So the converse of this is obvious. The Birkhoff ergodic theorem is much easier. Okay. So what do I mean by this? I mean that if T is not ergodic, the conclusion doesn't hold. And maybe I'll just say one more word. Consider the characteristic function of A, where A is a non-trivial T-invariant set. Okay, so if I'm not ergodic, there's such a set, and the Birkhoff ergodic theorem can never hold for such a, the characteristic function of such a set. The conclusion can't hold. So the Birkhoff ergodic theorem is saying sort of like a very natural, necessary condition, surprisingly is sufficient. Okay? let's continue talking a little bit about the Birkhoff ergodic theorem. And so for the remainder of today's lecture, we'll be talking about consequences of the Birkhoff ergodic theorem without proving it. And next lecture, which is tomorrow, I'll prove it. So let's consider the case of continuous functions. So let X comma D be a compact metric space. And I'll consider the Borel sigma algebra. Let T mapping X to itself be mu ergodic. If it helps you think of it as being continuous, and mu be a Borel probability measure, but we only need that T is measure preserving. I'm sorry, we only need that T is measurable. We don't need that it's continuous. There exists G sub mu with mu of G sub mu equal to 1, and the limit as n goes to infinity of 1 over n times the summation from I equals 0 to n minus 1 of f of t to the I of x equal to the integral of f du for all f and the continuous functions on x. Okay? Yeah, so let's take a minute to talk through what this is saying. It's saying that if I'm in a compact metric space, then there's a full measure set so that I get this convergence given by the Birkhoff ergodic theorem, not just for one function, but for all functions in some kind of nice class. The nice class isn't all of L1, but it's the continuous functions. Let me remark that the analog of this theorem for sigma compact metric spaces is true as well, but you want to replace continuous by continuous compactly supported functions. Okay? Let me make another remark, which is if you go back to the definition of generic points, this is saying that if mu is ergodic, there's a full measure set of generic points. So remarks. Improving quantifiers in Birkhoff ergodic theorem. Okay, the next remark is analogous theorem true. For sigma compact metric spaces. And then it says that if mu is ergodic, T is mu ergodic, implies there exists a full measure set of generic points. Generic points. And let me remark that there are many circumstances where every invariant measure has a generic point, and there's also lots of circumstances where plenty of invariant measures do not have generic points. So those are sort of two things that if you're not ergodic, there's no but you are invariant, there's no guarantee that you have a point that's generic for this measure, or even quasi-generic for the measure. Okay. Oh, let me make make another remark. So I've said that it's improving quantifiers in the Birkhoff-Ergodic theorem. Of course, we're dropping from all L1 functions to a restricted class, continuous functions. But under sort of big generality, you can't expect that there's a full measure set that works for all L1 functions. Indeed, if you're in a non-atomic measure space, you can just change your L1 function on a countable set, say the orbit of a point, and the integral is still the same. But by changing it on this countable set, say the orbit of my point x, I can prescribe this to be whatever I want and have whatever kind of limit points it wants, the limit exists, or whatever I want, and not change the right-hand side. So in the non-atomic setting, there's sort of no hope that this is going to be true for all L1 functions. This example is done in the notes, if that was a little too quickly for everybody. Okay, so let's talk through the idea of the proof of the theorem. All right, so what's the idea of proof? Okay, step one. C of x has a countable sup norm dense subset. Okay. So the first thing is continuous functions on a compact metric space have a countable set that's dense in the supremum norm. Everybody okay with this? For example, the notes sort of hum a few bars of what the proof of that would be, if anybody is interested in that detail. What's the next statement? Okay, so let G sub f, for each, let G sub f sub I be equal to the set of x, so that 1 over n summation from I 0 to n minus 1 of f sub I. Fusion of indices, t to the I of x, converges to the integral of f d mu. By the Birkhoff-Ergodic theorem, measure of G sub f sub j is equal to 1 for all j. And so, the measure of the intersection of G sub f sub j is equal to 1. Right? The intersection of full measure set, a countable set of full measure sets, has full measure. Okay. And what's the last step? So 3. If x is in the intersection from j equals 1 to infinity of G sub f sub j, then for any h in continuous compactly supported functions, 1 over n times the summation from I equals 0 to n minus 1 of gh of t to the I of x converges to the integral of h d mu. Okay, so that's how the sort of proof outline goes. First, there's sort of a countable set that's fairly rich in the continuous functions. It's dense in supremum norm. The second step is that if you just check the Birkhoff-Ergodic theorem in each one of these, that has full measure. And so I've gotten countability, so the guys that hold it for this entire countable sup norm dense set has full measure too. And then the conclusion of the Birkhoff-Ergodic theorem being true on a set of functions passes to its closure as well in supremum norm. So let's talk briefly about this. So what I can do is I can pick, since this set is sup norm dense, I can pick some f sub j that's extremely close to h. So each and every one of these terms is going to be, so f sub j of t to the I of x is going to be very close to h of t to the I of x. So the left-hand side for f sub j is going to be very close to the left-hand side for h. Similarly, the right-hand side for f sub j is very close to the right-hand side for h. And so having this true for all of the f sub j's gives it to you for the sup norm closure. Okay. The notes have this done in detail. Let me make a remark. You could try and imagine doing the same thing for L1 closure. And for the right-hand side, everything is delightful. If I make a small change of my function in L1 norm, the right-hand side doesn't change very much. The left-hand side could change a lot. In this example where I change my function on an orbit, and I don't even change what it is in L1, because L1 is actually equivalence classes, points this out. That, doesn't change, it points out the fact that the left-hand side doesn't play very nicely with L1 closure. It plays very nicely with sup norm closure, not nicely with L1 closure. Any questions on this? Okay. Yeah?
Can you repeat this a bit more slowly?
Oh yeah, thank you. Yeah, thank you very much for this question. It's a delightful fact, or a delightful thing. So let's talk through a little bit. Because there's something like this. So what am I trying to highlight? I'm trying to highlight that there's something a lot like this theorem's proof that's not true. If you replace the word sup norm closure with L1 closure, it's not true. And so where does it go wrong? Where does it go wrong? It goes wrong not on the right-hand side. So the Birkhoff-Ergodic theorem is about inequality. There's a right-hand side and there's a left-hand side. You can look at the right-hand side and say, oh, I changed a little bit in L1 norm. Life's still grand, right? But the left-hand side doesn't necessarily, the left-hand side could change a lot, especially for individual x's. Did that help?
Yeah, no, I understand the concept, I just, okay.
Yeah, okay, cool.
I didn't see.
Yeah, I should say the notes have this sort of yeah. Okay. All right. So, yes. Okay, so let's state one more. So at this stage, any other questions? Great. Oh, and maybe I'll just make a remark. So in the sigma compact setting where you replace compact spaces by sigma compact metric spaces, and the continuous functions by continuous compactly supported functions, and the sup norm you replace by the sup norm, the proof goes through exactly the same, and it uses that the continuous compactly supported functions have a countable sup norm dense set. Okay, and then every other step is the same. The other steps are sort of general. Okay. Oh, I did want to make one more remark. So if you have a set of functions that the Birkhoff-Ergodic theorem is true for, if you have a set of functions S that the Birkhoff-Ergodic theorem is true for, a point X, it is also true for X and we could take S and we could take its closure in sup norm. Not necessarily true for L1 norm, and it's also going to be true for the span of S. So any finite linear combination of S. I guess linear combination means finite linear combinations. All right. So let's now move on to discuss one more result. So one more result. So we have the following theorem. Let X comma D be a compact metric space. And now I really do want it to be in a kind of very special circumstance. I don't want it to be sigma compact. I want it to actually be compact, just as in the Krylov-Bogolyubov theorem. Be a compact metric space. T from X to X, it needs to be better than measurable, it needs to be continuous. Okay. If there exists exactly one T invariant probability measure and it's going to be convenient for me to name it mu, then for all f in the continuous functions on x and y in my space, the limit as n goes to infinity of 1 over n times the summation from I equals 0 to n minus 1 of f of t to the I of x is equal to the integral of f d mu. Okay, so in some sense this is an improvement on the previous theorem. Because not only do you get this on a full measure set, you get this on literally every single point. Now of course you have a very strong assumption, which is that there's only one invariant probability measure. Okay? And let me make one more remark. And this convergence is uniform in x and y. I'm sorry, my x should be a y. And this convergence is uniform in y. So what do I mean by its convergence is uniform in y? I fix my x in the continuous functions, and I fix an epsilon bigger than 0. Then there is a number m, so that for all m bigger than n, this average is within epsilon of the integral of f d mu. Let me write that out, because that's probably too much of a word jumble to process if you don't already know it well. That is all f and c of x and epsilon greater than 0, there exists relative n, so that for all n bigger than or equal to n, and y and x, the absolute value of n summation f of t to the I of x minus the integral of f d mu is less than epsilon, and my x should be a y again. Okay, everybody happy? That's what I meant by the convergence is uniform.
The point is generic, right?
Yes, yeah, so thank you very much. That's a great remark to say. So, remark. Every point is generic. Okay, so maybe I should blather a little bit about this. So this is a really cool theorem because ideologically, as an ergodic theorist, we want to use the tools of dynamics and measure theory to understand what's happening to orbits. And why not be very greedy? So mathematicians, we often are sensible and we do what we can first, but then at some point we get greedy and we always want to do more and more and more. So maybe it would be great if I could explain what happens to every single point. And in this situation, at least for the standpoint of the averages, you know what's happening for every single point. So it's a really strong, delightful conclusion. Everybody okay with that? Also, sometimes this is very helpful for applications. So sometimes when you're applying ergodic theory to get some kind of results, you care about individual points. For example, this often shows up in applications to number theory. There's sort of a point that's important, and points are just zero measure sets. So how are you going to get your conclusion for that? And so it helps to have a conclusion that's true for every single point. And usually that's not what happens, but in this circumstance, where you only have one t invariant probability measure and you're in a nice topological setting, so a compact metric space and your continuous map on it, then you have the conclusion for every single point. And then there's another remark, so this is called unique ergodicity. So in jargon, this is called unique ergodicity. And the second week of my lecture, where I move away from sort of the most basic ergodic theory, which is what these 3 lectures are about, will be about circumstances where you can establish unique ergodicity from some sort of flexible arguments. So, okay.
By unique ergodicity, you just mean that there is a unique ergodic measure, or you mean more conditions?
Yeah, so, okay, so this is a great thing. I think the terminology is often used a little bit ambiguously. So oftentimes it's used as a topological dynamical system term, which is when you want the assumptions of this theorem, and so you get the conclusions of this theorem. But you could also just parse the words. But usually I think when people use this, they mean this nice topological setting, where you get convergence of every point for every continuous function. Did that answer your question?
Yeah, so in your lecture series you will be using this...
It's not going to play a huge role, it's just sort of implicit in the lecture.
Okay,
Yeah, okay. Yeah, thanks for the question. But maybe this can help motivate what I'm doing. Okay. So maybe I will just sketch the proof a little bit quickly. So idea of proof. Okay. So what's the idea of the proof? The idea is to assume not. Assume not. And then, so what do I get? I've got a sequence of x1, comma, da, 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 in my space x, and numbers n1, comma, da, 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 going to infinity. So there exists an epsilon greater than 0 and an f in the continuous functions on x, so that for all j, the absolute value of the summation 1 over n sub j, summation from I equals 0 to n sub j, plus 1, of f of t to the I of x, minus the integral of f d mu.
xj.
Greater than epsilon, and it's fj, thank you, Krzysztof. And this is fj as well. Okay. No, I'm sorry.
No.
The f's are f's, the x is an xj. Thank you. Okay, everybody happy about this? Okay. And then, so the next statement is that I can consider the measures. So let nu sub j be equal to 1 over n sub j times the summation from I equals 0 to n sub j minus 1 of f of t to the I of x sub j. Can people see this last board pretty well? Okay. And let's let nu be a weak star limit. Of the nu sub j's. Okay. All right. Then what we have is we have that nu is t
So
in
instead of f, you should write Dirac measure.
Thank you, Krisha. Don't be sorry, thank you very much. Delta of t to the I x. Yes, sorry, thank you very much, Krzysztof.
XJ.
Xj, thank you. Okay, that nu is t invariant as in the proof of the Krylov-Bogoliov theorem. As in the proof of the Krylov-Bogoliov theorem, right? That's how we constructed our t-invariant measures. Okay, and then the next statement is that the integral of f d nu does not equal the integral of f d mu. Okay? Because weak star limits, the limit of the integral of a continuous function for the weak star limit is the same as the limit of the integrals, and that's basically the definition of the weak star topology. It's the weakest topology with that property. That's the definition. Okay, so that's the idea of this proof. Any questions on the proof? Okay, great. So next time I think this is probably a pretty reasonable stopping point. So next time I'll prove the Birkhoff ergodic theorem. And, yeah.
So do we have some questions, remarks, comments? So if no, thanks our speaker again. And let me announce the coffee break. So the coffee break is served